Hi everybody, welcome back. In this lecture we're going to get into weighted graphs and Kruskal's algorithm for finding the minimum weight spanning tree of a weighted graph. Let's start with the definition of a weighted graph. So a weighted graph is a multigraph together with a function on the set of edges which returns a positive real number for every edge in the graph. That function is called an edge weighting. Let's have a look at an example of a weighted graph. So we'll start with a graph. We'll just make one up here. So here's our graph, and we've got vertices 1, 2, 3, 4, 5, and 6. And then the weighted part of it is let's throw some values on the edges. And these are the weights of those edges. So maybe we've got a 21, a 35, 16, 79, 21 again, maybe 32, and 5. And so there's a weighted graph. It's a graph with an edge weighting as well. Now, what could be some interpretations of this? Well, the vertices could represent, for example, they could represent cities. And then in that case, what would the edges represent? Well, those could represent roads. And then the weights, that could represent the distances. And so we've got an interpretation of why we may want to consider a weighted graph. In this case, we can see, cities 1 and 6, they're very close to each other, but cities 4 and 5 are very far apart. What else could we use a weighted graph for? Well, instead of the vertices being cities, we could let them be junctions. And the edges could be water pipes. And the weights could be capacities. So how large the pipe is or how much water can flow through the pipe to a given instance. Alternatively, we can think of the vertices as servers. And the edges could be fiber optic cables. And the weightings could be bandwidth. And so there are just a few examples of why we may be interested in weighted graphs. So now that we have a weighted graph, we can talk about the weight of a graph. And so, for example, if G is a connected multigraph with an edge weighting, so it's a weighted graph, then the weight of it would just be the sum over all of the weights on the edges. And in particular, for any subgraph of G, the weight of the subgraph is obtained just by summing over the weights of all the edges in that subgraph. The minimum spanning tree or minimum weight spanning tree, I'll just add the word weight here. So the minimum weight spanning tree, also abbreviated as minimum weight spanning tree, so MWST. That is a spanning tree that has minimum weight. So the spanning tree that has the smallest weight of all the spanning trees. That's the minimum weight spanning tree. So let's look at these definitions in terms of another example. So we'll consider this graph. And I'll just put the edge weightings on here. I won't label the vertices. So maybe we've got a 2, a 2, a 2, 3, 3, and a 6, and another 3. So for this graph, what is its weight? So we'll call this graph G. The weight of G is just the sum over all of the weights of the edges. So we've got 2 plus 2 plus 2 plus 3 plus 3 plus 3 plus 6. So that's 6 plus 9 plus 6 are 21. So there's the weight of our graph G. What are some examples of spanning trees? Well, a spanning tree could be something like this. There's a spanning tree, and the edge weights are 2, 2, 2, 3. So we'll call this tree, we'll call it T1. And the weight of T1 is 2 plus 2 plus 2 plus 3, or 9. What's another spanning tree? We can choose something like this, and this, and this edge, and that edge. We'll call this tree T2. What are the weights? Well, that's a 2, a 2, a 6, and a 2. So the weight of this one is 2 plus 2 plus 2 is 6, plus 6 is 12. So there's a couple of spanning trees with their weights. This one has a smaller weight than this one. Is this the smallest weighted spanning tree of the graph? Well, we can go ahead and maybe look at all the different spanning trees there are, compute their weights, figure out which one's smallest. And it turns out that this one, T1, is a spanning tree of minimum weight. 9 is the smallest weight we can have. So this is a minimum weight spanning tree. But it's not the only one. So what is another? Another minimum weight spanning tree is, let's draw another one out. So if we took this edge, and this edge, so we took all of those 2's, and we also took this edge down here, which is a 3. So this tree, which we'll call T sub 3, the weight of it is also 9. So we've got, for this graph, we've got a couple of minimum weight spanning trees. Here's one, and here's another one. Both of them have weight 9. So this leads us to the question, how do we actually find a minimum weight spanning tree? Do we exhaustively go through all possible spanning trees, compute their weights, and figure out, oh, that's bigger than these ones, so I'd throw that one away. I'd only keep the ones with the smallest weight, and there was a couple here. Well, it turns out that there's a much more effective way to find minimum weight spanning trees, and it relies on a particular property of the minimum weight spanning tree. So we'll first cover the property, and then we'll look at the algorithm, which is known as Kruskal's algorithm, for finding a minimum weight spanning tree. So the main property that minimum spanning trees have is the following. If we split up the vertex set into 2 sets, so we partition the vertices into V1 and V2, amongst all of the edges with one vertex in V1 and the other in V2, let's let E be the one of smallest weight. It turns out that there is a minimum spanning tree that uses E as one of its edges. So here's the picture. So this isn't a complete picture, but this is the idea we'll have in mind, and then we'll prove this without really relying on the picture. So the idea is we've split up our graph into 2 vertex sets. And of all the edges that bridge these 2 sets, there's one of them, or there could be more than one, that has the same weight as it, but there's one of them of minimum weight. Let's call that edge E. So we'll let V1 and V2 be a partition of V, and E the edge of minimum weight with ends in V1 and V2. I want to show that there is a minimum weight spanning tree that uses edge E. So what we'll do is we'll let T be a minimum weight spanning tree. Now I don't know if T uses E or not, but I will show that if it doesn't, I can always find a minimum weight spanning tree that does use E. So let T be a minimum weight spanning tree, and just for the purposes of getting a visual of this, maybe this is what our spanning tree looks like. I just have to make sure I draw it so there's no cycles introduced. If E is on T, then we are done, because E is on the minimum weight spanning tree. So we are in the case otherwise. Suppose E is not on T. Well, if E is not on T, then there must be another edge in the spanning tree which goes from a vertex in V1 to a vertex in V2. So how are we going to find that one? Well, we're going to do the following. Suppose E is not on T, then we will add it to T. And that will create a cycle. So then T plus E will create a cycle, because adding an edge to a tree creates a cycle. So we'll let F be an edge on this cycle with ends in V1 and V2. So there's got to be this edge F that bridges these two vertex sets. And that's part of our tree T. So E is not on our tree, but F is. And now what I'd like to do is I'd like to show that I can always modify it to make a minimum weight spanning tree that does contain the edge E, and therefore doesn't contain the edge F. And the way we do that is we will consider the graph S, which I get by taking T, removing F from it, and then adding the edge E to it. So I've removed F and added E. What can I say about this graph S? Well, S is a spanning tree. Why is that? Why is it a spanning tree? Well, there's a couple of ways we can think about why it's a spanning tree. So what did I do? I added an edge, E, and I took away an edge on the cycle that E created. So I shouldn't have a cycle anymore, because I added an edge, it created a cycle, then I removed an edge from that cycle, the cycle's gone, so the graph should be acyclic. Another way to think about it is I've added an edge, the graph was already connected, I added an edge, it's still connected, that edge made a cycle. I removed an edge on that cycle, therefore the underlying graph is still connected, so S is still connected. So S is connected, it's acyclic. If either one of those we didn't really want to think about checking, we could have just said, well, I added an edge and I removed an edge. So it satisfies the relationship between the vertices and edges, that the vertices are the number of edges plus 1. So I think the simplest way to see this is S is connected because I added an edge, created a cycle, then removed an edge on that cycle, so that remains connected. And the number of vertices is equal to the number of edges plus 1, because I took a graph that satisfied that property already and added an edge, then removed an edge. So ultimately just left the edge count the same, and therefore this equation still holds. And so that means if it's connected and has that edge property, that's a criteria of being a tree. So it is a tree, and it uses all the vertices, so it's a spanning tree. Now what's the weight of this spanning tree? Now, the weight of S has to be less than or equal to the weight of T. Why is that? Well, what I did was I removed an edge and replaced it with edge E. But of all the edges that bridge from V1 to V2, E was the one of smallest weight. So I know that the weight of E is smaller than the weight of F. And so that means, since the weight of E is smaller than or equal to the weight of F, then when I remove F and replace it with E, I'm replacing an edge of smaller weight, so my S has to have smaller weight than T, or less than or equal to. It doesn't have to be strictly smaller, because these guys might have the same weight. And so what does that mean? Well, we have but T is a minimum weight spanning tree. So the weight of T has to be less than or equal to the weight of S. And so I have these two inequalities. The weight of S is less than or equal to the weight of T, but the weight of T is less than or equal to the weight of S. And so therefore, we have that the weight of T is equal to the weight of S. And if T is the minimum weight spanning tree, so is a spanning tree that has smallest weight, well, S has the same weight, so it must also be a minimum weight spanning tree. So therefore, S is a minimum weight spanning tree which contains E. And so we're done. We found a minimum weight spanning tree that contains the edge E. Now this lemma is important for two reasons. So one, the statement of the lemma is important, but on the other hand, also the proof of the lemma is important because we can adapt this in other situations. Specifically, this lemma and its proof will allow us to establish the validity of Kruskal's algorithm for finding a minimum weight spanning tree. Now I'm not going to provide the details of why this algorithm works here. It basically follows from that previous lemma and its proof. The details of the proof I've also left in the lecture notes booklet so you can see the full details. But here we'll just go through what the algorithm says and then an example of how it works. So Kruskal's algorithm for finding a minimum weight spanning tree takes as input a multigraph with an edge weighting, and what it returns is a minimum weight spanning tree of G. The way it does this is it does it by what's known as a greedy approach. So what's a greedy approach? Well, that is, or a greedy algorithm, is one that at every step just takes the best possible choice. And what's best possible in this case? Well, we're trying to find the minimum weight spanning tree, so we just choose an edge of lowest weight. So we choose an edge of what we call cheapest weight at each step. And that's it. We just at each step choose the edge of cheapest weight. Now, of course, we're trying to make a spanning tree, so we make sure we choose an edge that doesn't create a cycle. But other than that, we're free to choose the edges how we please in the cheapest way possible. So here are the details. So we set E star to be the set that's going to contain the edges of our spanning tree. It's empty to start with. Then we sort the edges from least weight to greatest weight. So from cheapest to most expensive. While V with this edge set we're building is not connected, so in other words, while this object that we're trying to make into the spanning tree is not connected, do the following. And notice we've already set the vertices to be all of the vertices in the graph. So we're adding edges until this thing becomes connected. We set E to be the next smallest edge in our sorted list of edges. If it creates a cycle, then we throw it away. We only keep it if it does not contain a cycle. So then we add our edge to our collection of edges and update our edge set. And we just keep doing this. Find an edge of cheapest weight, throw it in there, until we end up with a connected graph in the end. And that will be our minimum weight spanning tree. So let's see, how can we do this in practice? Well, we're going to do it right on this graph, and you'll see it's very quick to do Kruskal's algorithm. So we want to pick the edge of smallest weight. There it is, of weight 1. So that edge is in our minimum weight spanning tree. So as you'll notice, I've only put edge weights on the edges. I haven't labeled the edges. I haven't labeled the vertices. This is just to focus our attention on the weights themselves. So what's the next cheapest edge? Well, there's an edge of weight 2. So that's the next cheapest in the bunch. And so we're going to select that one. There's no other edges of weight 2. What's the next cheapest edge? Weight 3. But I can't add that in because it will create a cycle. So then I go for the next cheapest edge. What is it that I can add and not create a cycle? Oh, there's an edge of weight 4. I can add that in. The next cheapest one is 5. I can add that in. I can't add 6 in. That's the next cheapest one because it will make a cycle. What else can I do? Oh, I can add the 7 in. That won't create a cycle. I can add the 8 in next. I can add the 9 in. Notice in this example, all the edge weights are different. If there were edges that were weighted the same, then we're free to make the choice however we want. We could pick any of them. If there was a bunch of them of number 9, we could pick any one of them as long as they don't create a cycle. So then we are now picking edge 9. There's no other edge weights 9. The next one I'm going to pick is, there's a 10. And there we go. Our graph is connected. And so we found our minimum weight spanning tree. And there we go. We've shaded it in there. So that's the spanning tree of smallest weight. We can go ahead and find the weight of it. Let's call it T. And so then we can go ahead and work out what is the weight of T. The weight of T is 1 plus 2 plus 4 plus 5 plus 7 plus 8 plus 9 plus 10. A nice quick way to add these numbers up would be, there's a 1 and a 9, so that's a 10. 8 and 2, that's another 10, makes 20. So another 10 is 30. And then I've got a 9 plus another 7 is 46. And so we found a minimum weight spanning tree, and the weight is 46. All right, so that's it for this section. Thanks very much for watching, and we'll see you again next time.